Now, we're going to look briefly at the scene labeling, the segmentation problem. Scene labeling aims to relate one semantic class as road, water, sea to each pixel of the input image. A major problem in scene labeling is the fact that the algorithm must take into account the global organization of the picture to predict each pixel, since, for example, it is really unlikely to observe one pixel of road between two pixels of water. Several attempts to try to solve this problem of long-range dependencies between pixels by using recurrent convolutional neural networks. In the first paper, the identical CNNs are applied recurrently to the output maps of CNNs in the previous iterations. By doing this, the method achieves slightly better labeling results while significantly reducing inference times. The algorithm is then able to smooth its prediction over the numerous iterations because it takes as input the original image and the predictions at previous iterations. DEG, recurrent neural networks designed in 2016, can also be used for scene labeling. They use the recurrent neural networks to model the contextual dependencies among image pixels, thus dramatically boosting the labeling performance. In Deep Lab, pixel labels are first generated using deep CNNs. Then they use a probabilistic technique, conditional random fields, to post-process the information given by the CNNs to, in turn, boost the labeling performance. Here are two images which have been segmented using classical CNN and DAG-RNN, the ground truth being the last picture. When a classical CNN is used, the scene labeling is not smooth. You obtain incorrectly labeled pixels inside large areas. This phenomenon diminishes when DAG-RNN are used, since they take into account the spatial dependencies between pixels. Areas are more homogeneous and there are less incorrectly classified pixels lost in the middle of big areas.